and I will mute the other guys. Okay. Okay, please check if this cell run properly. And please let me know. Okay, during the downloading the data set, first one is dataset description. We will use Flickr 8K for training and subset of MS Coco for evaluation. Flickr 8K is a labeled dataset consisting of 8K photos with 5 captions for each photos. It includes images obtained from the Flickr website. And MS Coco is a large-scale object detection, segmentation, and captioning dataset. And it also contains photo with 5 captions for each photo. But the size of the dataset is much larger than Flickr 8K. So we use only subset of the MS Coco. And MS Coco stands for Microsoft Common Objects in Context. And the image below is from MS Coco dataset. You can explore the MS Coco here in the link. Sorry, can I get the attendance link again? Oh, okay. Thank you, Taki. And there, for example, for captioning this image, there are various ways to caption. And for this image, there are 5 captions, as I already said. The orange cat looks at a television set in a chair. A cat on a wood floor watching a TV sitting on a chair. Oh, cool. Okay. Can you run this cell properly? It works? Oh, thank you. And actually, there are 30K. There are another version of Flickr named like Flickr 30K, but if you download the file here, you will get only full version of 8K and subset of MS Coco, but not the Flickr 30K. So next session is preprocessed image captioning data. And if you followed well the practice session before, there were many image preprocessing code. So you will maybe you guys used to these things. Okay, preprocess data set and cache them into local disk. Create input files for training, validation, and test data. For image, we are using a pre-trained encoder. We would need to process the images into the form this pre-trained encoder is accustomed to. Okay. The pixel values must be in the range 0 to 1, and we must normalize the image by the mean and standard deviation of the ImageNet images RGB channels, like this, for RGB channels. And we'll resize all the images to 256 by 256 for uniformity. Yeah, it is not mandatory, but we want square matrix of NumPy arrays. So we resize it into square matrix, which has length 256. And for the text data, we will tokenize sentences and add special tokens. For example, for the sentence, a man holds a football, and if we tokenize it, you can get the tokens like this. At the beginning, the token SOS or star token, and it ends with end token, and the remaining part, I mean at the remaining part, the max length minus number of tokens of pair token exists. Okay. Okay. So to pre-process the image captioning data, just simply running it, and I will comment something. Okay, this part, where is it? Actually, MS Coco and Flickr is different, distinct data sets. So we have to manually pair the image and caption data for use the caption of MS Coco to Flickr 8K dataset. So this is a manual pairing process with for loop, and we have to create vocab because this is just for sanity check, to check whether if you download and import the data set properly. And this block of code is create vocab, and as you saw before, you have special token like start and pad or something. So you have to add this kind of special tokens to vocab. And this is for creating vocab. Okay. And save the vocab map into a JSON format. And okay. And sample captions for each image, and save images to HDF5 file, and captions and their lengths to JSON files. What is HDF5 format for? This is kind of file format to store very big NumPy array or torch tensor type data. So if you want to use Flickr 8K is kind of large data set, unlike the MNIST or FMNIST you used usually. So by utilizing this HDF5 format, you can properly control or treat the large data set. Yeah. And by running it, you can end the pre-processing task. Okay, next step is defining PyTorch dataset class. First one is reading. Okay. Open HDF file and image are stored, where images are stored, and captions per image. By this part, read image from the HDF5 file that you already saved at the code block above, and transform the images, and by and for the get item method with get item method in the caption dataset class, you can pop the data instance, a single data row of a single row of data. I mean while iterating the data set in the data loader. So you have to define the get item method, and There could be a question. How about this part? There were what? There were several not colored images in the image dataset. So, but unlike the colored image, or gray or black white image consists of just one channel, because colored image has 3 channels for red and green and blue. So we have to manually expand the channel from 1 to 3 by just copying it, copy and pasting it. So this is the code for processing the grayscale image. And then next part is implement show, attend, and tell. The image encoder. This encoder encodes the input image with 3 colors channels. I mean the images with 3 channels into a smaller image with learn channel. There are actually the Flickr dataset, the images we already transformed into fixed size of 256 by 256 has specific height and weight, right? Which equals to 256, but we expand the channel and reduce the height and weight, width, height and width. So expand the channel to 2048 from 3 and reduce the height and width to 14. With this pre-trained encoder of ResNet 101. But the thing is, we have to convert these images into a representation of the vector, and we don't want, that's what we only want, and we don't want to classify it into certain class. But in ResNet 101, at the last part of ResNet 101, there are several classifier module. So you have to get rid of it. Okay, these smaller encoded images are a summary of representation of all that's useful in the original images. Due to the VRAM limitation of Colab, we will use ResNet 101, which is described in the top figure, instead of VGG 16. Actually, this is VGG 19, but VGG 16 is much larger size than ResNet, so we will use ResNet 101 instead. And since, as you can see, all this convolutional neural network structure have classifier at the last side. And in ResNet 101 case, there is, after the average pooling the representation of vector made by convolutional network, you classify this representation of vector into 10 class. 1,000 class, yeah. So we have to get rid of it, and that is exactly what you have to do. I will give you 5 minutes for I will give you 10 minutes for filling this blank, you have to load the pre-trained ImageNet resonant 1.1 here and get rid of the top two layers in the model for deleting the classifier and only get the image encoder for representing the Flickr 8K image dataset. Okay, I will give you 5 minutes for filling these 2 lines of code. Okay, let's move on. It's already 11:02, and to load the pre-trained resonant 1-1, ImageNet resonant 1-1, you can simply put a single line of code like this, but you may wonder this progress argument. This is for just using Colab. Without this, it may result the error. And after loading the pre-trained resonant 1-1, you have to get rid of the classifier at the last part. And like this. And some guys may wonder what this adaptive underbar pool is for. In our case, we recite the all images in the data set to a square shape like 256 by 256, but so it works as a usual average pooling layer. But with this adaptive average pooling layer, you can apply the average pooling into variable length data. But we have no variable length data. We have uniform length data. So this is implemented for the generalization to other data set. So for class encoder, there are you can fine-tune the pre-trained encoder, and please, next one is please implement the two part in 5 minutes. First part is freeze the encoder parameters, and second part is freeze it. No. Fine tuning, unfreeze it, make it trainable for only for the high level feature encoder. You can get the list of high level feature encoder layer by this iterable. So to simply put, the first part is for freezing all the parameters in the loaded pre-trained encoder, and second one is for unfreeze it again only for the high level feature encoder. Okay. I'll be back in 11:10. for Sangha. So with adaptive average pooling layer, whatever the input size, you can fix output size. Yeah, right. By properly control the kernel size and stride automatically in the model, adaptive average pooling model, you can get the fixed size output you want. Okay, it's quite useful. Okay, if you notice that we want to fine tune the model, we want to fine tune the last parts of the model, loaded model, when only when the fine tune argument is true. You can, if you figure that out, then you can properly implement this code. Okay. First, to freeze the what is it? To freeze the model, you can in the class encoder class, there are ResNet. You already pre-trained, you already loaded, and by referring the self.resonate and referring the property of that self.resonate by parameters, and you can refer the parameters in the self.resonate, right? And by setting the property of requires grad of the parameters into false, then it will be freezed. So call the parameters in the self.resonate and freeze it by this code. And if you want to fine tune the model, if you want only the fine tuned high level feature encoder, Then please go to last 5 parts of the fine-tuned model of the pre-trained model and get the parameters of it and use this use this fine-tune argument Boolean value. So if you don't want to fine-tune the last part, then you maybe this input will be first, and p dot requires grad equals false means it is still freeze, right? Okay. So there could be a question. Why do we only fine-tune the high-level feature encoder, not the low-level feature encoder? Because we want to fine-tune the model into pre-trained model in with Flickr 8K dataset, and our pre-trained model is trained with already pre-trained with ImageNet. And the low-level feature, there will be basic element to represent the image properly. So at the low-level feature, there are and there would be basic feature of the image, and the high-level feature. At the high-level feature, there will be various kind of there will be variant according to the data set. So high-level feature in the data set in the Flickr 8K dataset and ImageNet dataset may differ, right? So we only fine-tune. We have to and we want to conserve the generalization power of our pre-trained encoder. So we only fine-tune the high-level feature encoder. Okay. That is what this line of code for. And next part is attention network. The attention network estimates the importance of a certain part of an image. It considers the sequence of generated thus far and attends to the part of the image that needs describing next. Okay, and this is encoded image with this is image encoded with the pre-trained encoder ResNet 101. And by inputting this encoded image and previous output of decoder to the attention network, we can get the weight of each region. Then what regions have higher weight, and encoded images weighted, indicating where the decoder should pay attention to generate the next word. So by using this image and this area, this white shaded area, decoder can generate the next token better. Okay, we will use a soft attention, not the hard attention, where the weights of the pixels add up to 1. So if there are p pixels in our encoded image, then at each time step t minus and then each time step t, this entire process is computing the probability that a pixel is a place to look to generate the next word. Okay. Hard attention, as you know, as you already know, hard attention is like a one-hot vector, but soft like that. So soft attention is soft attention looks like sum-to-one vector, you know. So what you have to do is implement this number 4 style of attention in this class attention model. So by using these properties, implement first get the encoder feature and decoder feature and use attention between encoder and decoder feature and result, and get the attention weighted encoding. And you have to be careful about the shape of this tensor. So I already wrote it here. So I will give you 5 minutes for this block. Okay, let's move on. This is encoder feature. You can get it by pass encoder output through the encoder map. And the shape of it is like batch size by pixels, number of pixels by attention dimension. And this is for image, and this is for tokens, right? A decoder feature is you can get the decoder feature by passing the decoder hidden feature, hidden tensor to decoder map. And the shape of it is like batch comma attention dimension. And you want to operate something between this encoder feature and encoder feature and this decoder feature, but the shape of them are different, right? So you have to trade it by this unsqueeze operation. This unsqueeze will add the single dimension at position number 1, index number 1 here. So after the unsqueeze operation on the decoder features, you can add the encoder feature to add up the encoder feature and decoder feature, and by passing it through the ReLU network, and then you can get the full you can get the full attention score, right? And after passing it through the softmax function, but the softmax function should work in this non-pixels dimension, not the batch size dimension. You wanna do the softmax. You wanna get the score between the pixels, not the images, right? Between pixels, not the different images, distinct images in the data set. So you have to set. So that's why I set the dimension equals number 1 in this part, and you can get the attention weighted encoding like this, and please return it. And next part is text decoder with attention network. The decoder's job is looking at the encoded image and generate a caption word by word. Since it's generating a sequence like this, so we'll use recurrent neural net. And setting with attention, we want a decoder to be able to looking at different parts of the images with the attention module. For example, if you get the token and the attention network depicts the area you have to focus on, and this area means the man. So by inputting this token and input token and attention network's output to the decoder, and you can get a man token. More easier than before by using the attention network, right? Okay, instead of the simple average, we use the weighted average across all pixels, with the weights of the important pixels being greater. This weighted representation of the images can be concatenated with the previous generated word at each step to generate the next word. Okay. But this is just a simple trick for enhancing the performance, but the thing is this part. Okay, attention network let you know which part to focus on, right? So we'll manually implement padded sequence like this and text decoder with attention in this section. Okay. But the core part of attention show, attend, and tell is already covered. And by running it, you can get the packed padded sequence, the function for creating a padded sequence, and you can train it. In this section, we'll train the model and evaluate its performance with Blue Foursquare. And you have to firstly, you have to set the hyperparameters and utils. And by altering the foremost part for importing dataset, this maybe the system.path change it. So I added this part for explicitly defining the function like average meter and clip gradient, adjust learning rate, and accuracy in the utils package previously. So load Python libraries and set some hyperparameters, and here we will use NLTK, natural language toolkit library, to calculate the blue square. Okay, just running it, and we, based on that hyperparameters, we can properly train the model, pre-trained model. And we'll implement the objective function and single training loop in paper. The mathematically speaking, the objective function, mathematically expressed objective function is like this: negative log likelihood and some regularization term. So defining the train function by this, and you can validation code like this. We'll evaluate the trained model with Blue Foursquare. And by running the main function, you can do both training and evaluating the model. Maybe if this device is properly set, you get the error. But please run it first. And it would take around 8 or 9 minutes to train the model for one epoch, single epoch. So during the training, let's move on. Okay, next part is generate captions and visualize attentions. There are various ways to generate the tokens of sequence, right? The greedy decoding, choose the word with the high score and use it to predict the next word. But this is not optimal because the rest of the sequence hinges on that first word you choose. So if that choice is the best, everything that follows is suboptimal. By incorrectly choosing the first token, the foremost token. So, and it's not just the first word. Each word in the sequence has consequences for the ones that succeeded. So you'd better cover the larger area for generating the sequence. And that's exactly what beam search is for. It would be best if we could somehow not decide until we finish decoding completely and choose the sequence that has the highest overall score from a basket of candidate sequences. Beam search does exactly this. So it completely covers the greedy decoding span. And I prepared okay. And this in this section, we'll implement beam search decoding scheme. Okay, first part, just set the device as before. And this part is defining the caption image beam search function. So this K is hyperparameter, and if you want to increase the K, this height of the rectangle would increase as well, right? And if you want to cover more larger parts of the search space, then increase the K, but you will at the cost of increasing K, the generating speed will decrease, right? And if you set the K, if you set the beam size and read image and process the image and encoding it and flatten the encoding, and we'll treat the problem as having a batch size of K. So this is the most different part with greedy decoding, because there are no top K score in the greedy decoding scheme, right? You get only the best score, the element with best score in the greedy decoding scheme. But in this section, you have to initialize the top top K scores tensor, and after the calculating the K scores, after the calculating of all elements, you can get the top K1, and only that top K1 will be used at next iteration, right? And by using that, you can decode it properly, and it's way more better than greedy decoding. So this is the last part. It's only for visualizing. So I will give you 10 minutes for this. No. I will give you 5 minutes for this. Okay. Okay, this is actually last part of the practice session. After you get the score by putting the decoder output into log_softmax function, you can get the scores. And we already initialized those top case scores and expanded to shape scores, shape as score, and add the score to top case score. It is just for just only for converting shape, and this fill the values in the top case scores. For the first step, this case, all key points will have the same scores, the same previous words, HC. So, but otherwise, unroll and find top scores for a step for the steps which is larger than 1, unroll and find top scores and their unrolled indices, and that convert unrolled indices to actual indices of scores. And by adding the new word to previous word, you can get the sequence and sequence alpha in this scheme, beam search scheme. Oh. Yeah. And you have to determine, you have to know whether if already reached the EOS token and token. So by using incomplete indicates indices and complete indices, you can do it. And next part is already implemented. Okay, set aside complete sequences and proceed with incomplete sequences, and doing this until you get the EOS token. Using this, iterate this several lines of code until you get the EOS token for all the possible cases, which is enabled by while true. Okay, and then you can simply visualize the attention. Okay. Instead of investigating the true impact of attention score on each input images, we use some trick to visualize attentions on the input image and resize the image to this scale, and expand our 14 by 14 attention score matrix to this scales as below. Expanded attention metrics are acting like a regional mask input image. So this is adapted by others repo here, and you can simply visualize the true impact of attention by running this code. And okay, if you met any kind of errors, please let me know. And this is end of the sessions, and I will hope you guys have a nice year-end party. So okay, this is end, and if there are any questions, please leave the message in the chat box. I'll wait for 5 seconds and okay, thank you for attending this practice session and have a nice year end. Okay, bye-bye. See you soon. Oh. Decoding the same. Is greedy decoding the same with what we used at transformer? You mean the transformer practice session? Um, I don't know what you actually did in the transformer section, but if you want, if you generate only one possible case of sequence, then you may choose the best token for each set, then that's kind of greedy decoding. So oh really? I think I thought I answered already. I answered it already, but maybe my voice is muted, right? So I will let you know why we get rid of the top two layers of the pre-trained resonant 101. Because you mean the top two layers means you mean the classifier layers, right? What we want to do is only make representation vector from using image with the pre-trained image encoder, but we don't want to classify it into certain class in the ImageNet. ImageNet has 1,000 class of ImageNet has 1,000 classes in it. And in original pre-trained ResNet 101 structure, there are some module or layers at the last part for classifying the representation vector, and we don't want it. We don't want them. So that's why we were getting rid of the last two layers from the ResNet 101. Simply put, we don't want classifier. We don't want classify. We only want represent the image and low high dimensional latent space. Okay. Okay. Okay, any other question? Okay. Again, I hope you guys have a nice year end, and I'm really thankful for attending this practice session. Okay, bye bye.